Okay, get ready for an idea that might just bend your brain a little. How can a piece of code solve a problem by calling itself? I know it sounds like a paradox, right? But it's actually one of the most elegant and honestly most powerful ideas in all of computer science. So today, we're going to pull back the curtain and demystify this amazing concept called recursion. I mean, really think about that for a second. How can a problem contain its own solution? It's a totally different way of thinking. The whole idea is that the solution to a really big, hairy problem actually depends on solving smaller, identical versions of that same problem. All right, so let's put a pin in the formal definition. At its core, recursion is a programming technique where a method literally calls itself. So instead of using a classic for loop or while loop to repeat something, the function just runs itself again. And each time it does, it tackles a slightly smaller piece of the puzzle, just chipping away at the big problem until, poof, it's solved. You know, the absolute best way to picture this is with those Russian nesting dolls. You've got the big one, right? And to get to the very last, tiniest doll, what do you have to do? You have to open the current one, and what's inside? A smaller, identical version of itself. Recursion is exactly like that. It keeps opening the problem to find a smaller, self-similar version inside.
Okay, but wait. This whole calling itself thing sounds a little dangerous, doesn't it? Like it could just go on forever? And you're right, it could. So for recursion to work safely without, setting your computer on fire, it has to follow two golden rules. These are non-negotiable.
So every single recursive function is built from two key ingredients. First, you've got the base case. Think of this as the emergency brake, the stop sign, the "we're done here" moment. It's the condition that finally tells the function to stop calling itself. Then you have the recursive case. This is the engine. It's the part that says, nope, not done yet, and calls itself again, but, and this is crucial, on a slightly simpler version of the problem, inching its way closer to that base case.
And I am not kidding when I say that base case, that exit strategy, is everything. If you forget it, well, your function becomes an unstoppable force calling itself over and over and over, an infinite loop. Your computer desperately tries to keep track of every single call, it runs out of memory, and boom, it crashes with that infamous Stack Overflow error. So yeah, the base case is pretty important.
All right, enough theory. To really, really get this, we need to see it in action. So let's go down the rabbit hole. We're going to trace a classic example step by step and watch how a recursive function solves a factorial problem right before our eyes. So the problem we're tackling is super simple. Calculate 3 factorial. 3 times 2 times 1. We all know the answer is 6. The interesting part isn't the what, it's the how. How does recursion figure this out? Okay, here we go. The whole process kicks off when our main program calls factorial of 3. But here's the thing. Factorial of 3 can't give an answer yet. It says, hold on, to solve myself, I need to know what factorial of 2 is. So it hits pause in itself and makes that call. Well, guess what? Factorial of 2 does the same thing. It says, I can't solve this until I know what factorial of 1 is, and it also gets paused. This chain continues until, finally, we call factorial of 1, and that's our base case. It knows the answer. It doesn't need to call anyone else. Yes, we've hit rock bottom, but in a good way. We've reached that smallest, simplest, solvable piece of the puzzle. The chain of waiting calls has finally reached the end. And now the real magic begins. The whole thing starts to unwind, and all those paused functions can finally get their answers. So watch this. Factorial 1 knows its answer is just 1. It hands that 1 back up to the factorial 2 function that's been patiently waiting. Factorial 2 says, awesome, thanks. It calculates 2 times that 1 it just got and gets a result of 2. Now it can finally finish its job, and it hands that 2 back up to the original factorial 3 call. And finally, factorial 3 gets the piece it's been waiting for all this time. It calculates 3 times that 2, and it returns the final result back to our main program. And what's that final result? 6. Exactly right. The answer was built piece by piece as the chain of calls resolved itself, all the way back up to the top. So that was a pretty simple example, right? But don't let that fool you. This fundamental idea, breaking a big problem into smaller versions of itself, can be used to solve things that are just mind-bogglingly complex. So let's see what happens when we really level up. Now, in our factorial example, each function call only made one more call. It was a straight line down and a straight line back up. But what if a function needed to call itself twice to get its answer? Or 3 times? What would that even look like? Well, what you get is something called tree recursion. Instead of a simple chain, the calls start branching out, creating a structure that looks, well, like a tree. A famous example is calculating the Fibonacci sequence. Remember that one? Where each number is the sum of the two previous ones. To figure out, say, Fibonacci of 5, you need to know 4 and 3. And to know 4, you need 3 and 2. You can see how it creates this huge branching cascade of calls. This is where recursion really starts to show off its power. And this whole branching idea, it's the key that unlocks elegant solutions to some really cool problems. Imagine trying to solve a maze. You could write a recursive function that says, at every intersection, try going left, then try going right. It explores every possible path. Or how about drawing those incredible, complex fractals, where every little swirl is a perfect, tiny copy of the entire image? These are the kinds of problems that would be an absolute nightmare to code with loops. But with recursion, the logic becomes surprisingly simple and, well, beautiful. But look, this isn't just some cool party trick for computer science nerds. This way of thinking is the backbone of some of the fastest, most efficient algorithms we have. This is where theory turns into serious speed. Yeah, there's a name for this whole approach, and it sounds as powerful as it is. Divide and conquer. It's a three-step dance. You divide the big problem into smaller, more manageable pieces. You conquer those smaller pieces by solving them recursively, and then you combine their solutions to solve the original big problem. That is the secret sauce. That is the magic behind so many high-performance algorithms. Let's make this super clear with an example. Imagine you have a huge, sorted phone book and you're looking for Smith. A linear search would be like starting at A and reading every single name until you hit Smith. So slow. A recursive binary search, on the other hand, is way smarter. It opens the book right to the middle. It sees Miller. It knows Smith comes after Miller, so in one move, it just tore out and threw away the entire first half of the phone book. It cuts the problem in half with every single step.
The difference in speed here is just staggering. It's not just a little faster, it's a whole different universe of fast. In computer science, we call this efficiency O log n. Now, that sounds complicated, but all it really means is this. If your phone book grows from 1,000 pages to 1,000,000 pages, the number of steps to find a name barely even goes up. It's an unbelievably efficient way to scale, and it's what makes searching through millions of items feel instantaneous.
And this divide and conquer magic isn't just for searching. Oh no, it also powers one of the most powerful sorting algorithms out there, merge sort. It works by recursively splitting a messy list in half, over and over, until you're just left with little piles of one item, which are, by definition, already sorted. Then it cleverly merges them all back together in perfect order. It's just an incredibly fast and reliable way to sort gigantic amounts of data.
So when you boil it all down, what's the big takeaway here? It's that recursion is so much more than just a coding technique. It's a mindset. It's a way of looking at a huge, intimidating, complex problem and just knowing that somewhere buried inside is a simple, tiny, solvable version of it. That's your base case. And if you can find that, you've found the key to solving the whole thing.
So I'll leave you with this question. Now that you've seen how it works, where else could you use this? The next time you're facing a massive project that feels totally overwhelming, try thinking recursively. Forget the whole thing for a second and just ask, what's my base case? What's the one tiny, simple thing I can do right now to make progress? And then, how can you break the rest of the big, scary problem into smaller versions of that same task? Give it a try. You might be shocked at how this divide and conquer thinking can work not just in code, but in life.